Hello. Today I would like to present the work conducted at the Integrated Actuators Laboratory. The title of this work is called a self-biasing shape memory alloy gripper for lightweight applications. So before I continue, I wanted to first present a small introduction on the key aspects of this work. The actuator is powered by a shape memory alloy, which is a type of smart material. And these smart materials are a type of material that reacts mechanically when exposed to some kind of certain stimulus, like a current or a magnetic field. So these materials are often used in applications where we require very lightweight or compact systems. And especially in the case of shape memory alloys, as they have the highest work density among all the other smart materials. So when we want to design a very lightweight solution, these alloys really offer the most work for the least quantity of material. So these shape memory alloys are a type of smart material that reacts to heat. So when they're exposed to a certain temperature threshold, they react mechanically. Here we see the work cycle of the alloy, and basically at low temperatures, they can be deformed quite easily. And when they're deformed, they also keep their shape. In a sense, they can be deformed plastically at low temperatures, but as soon as we heat the material above a certain temperature, all the deformations that we imposed at the low temperature state, it's removed and the material returns completely back to its original shape. So this behavior is often referred to as the shape memory effect. So as the material needs to be deformed before it can activate the shape memory effect, we need to pair the material with some kind of biasing element to create an actuator. So generally these biasing elements are passive springs. As you can see in the diagram, the spring is attached to the SMA so that the spring deforms the material at low temperature using the spring force. And that means that when we heat the material and activate the shape memory effect, the SMA will contract and deform the passive spring. As you can see, this results in a very simple but compact linear actuator. So here we can see the various subsystems present in a traditional SMA actuator. And the simple actuator I mentioned before only moves in a very simple linear motion. So if we need more complex movement from our actuator, we need to design a kinematic stage that will transform this simple linear movement into the required complex one. As you can see, these subsystems are generally like discrete blocks, and due to this, all these separate blocks increase the overall weight and complexity of the actuator. So often there isn't any conscious effort to integrate these subsystems into the actuator. So by doing so, we hope to preserve the high work density of the SMA actuators. So the goal of this work is to find and fabricate a way to integrate the kinematic stage and the biasing element of the so-called traditional SMA actuator. And so by doing so, we hope to create this self-biasing kinematic stage presented in this work. So it basically allows one subsystem to fulfill the roles of two. And the hope is by doing so, we can create an SMA actuator with a higher work weight density. So the basic approach to creating this new, more integrated system is to use compliant or flexure-based structures as the kinematic stage. The main advantages of these flexures are the fact that they can be created as a monolithic device, which means that they can there's less assembly time and there aren't any moving parts, and so there's less wear and tear, so better fatigue life. The main drawback of this system is the fact that when compared to traditional bearings and hinges, they come with some kind of inherent stiffness. So it's not some additional force is required to rotate this flexure-based hinge. But in this work, we hope to harness this inherent stiffness and use it as the biasing element for our SMA actuator. So the main challenges of this approach is that designing such a kinematic stage that can produce very complex output movements are not trivial and require some considerations. And these flexures, when deformed at large deformations, can result in an unwanted parasitic movement. And also, sizing the structure for the SMA can be actually quite difficult without creating an appropriate analytical model. So to overcome this design challenge I mentioned, in this work we use topology optimization to create a compliant kinematic stage that is able to take a single input from the SMA, shown in blue, and create a more complex radial four-prong output that's shown in black. So the goal of this structure is to be able to group circular objects using just a single input. So, however, the use of this distributed compliant hinges is not very optimal, and the structure generated is actually quite stiff. So, and also, if we want to adjust the stiffness of the structure, it's not easy, as there's not any easily adjustable parameters. So we use the kinematics obtained from the algorithm and adapt it using hinges made out of flexure-based pivots, so that we can easily size and alter and create the desired stiffness and strokes. So in this work, we also further adjusted the kinematic stage to have a stroke amplification in addition to the complex output, complex radial output. So one of the drawbacks of the generated structure was that there were some unwanted degrees of freedom. However, using the 2.5D design, we basically create flexure-based stages that can be added one on top of the other, so that we can constrain some of these unwanted degrees of freedom. So we can see layer 1 and 2 are basically the kinematic, the self-biasing kinematic stage, and layer 3 is another flexure-based stage that prevents unwanted rotation of the structure. So as you can see, so each layer has a specific role, and the final goal would be to create a kinematic stage that can transform the single input into a multi-output radial gripper system. So as mentioned previously, creating an analytical model of the system is actually quite important for sizing the final SMA gripper. So here, using pseudo-rigid models, the analytical model of the self-biasing kinematic stage is created, and this model is actually further validated using a pull tester and obtaining experimental results. The details could be seen in the paper. The stroke and force of the gripper can be estimated using the force displacement curves of the SMA and the analytical model of the biasing element that we just described. The curves of the hot and cold SMA are plotted separately, and the intersection of these curves with the biasing element will give us the operating points of the actuator. So by extrapolating these points, the stroke and the gripping force of the final actuator can be deduced. So this is the methodology that we use to find the final stroke and gripping force of the prototype. So the final prototype was fabricated using nylon and with 3D printing. So the whole structure is actually created from a single piece, and a single SMA coil is used to activate the gripper. The final gripper can output a force of 1.8 newtons and a stroke of 4 millimeters per prong. The total weight of the gripper is only 17 grams, which gives it a total force weight density of 105 newtons per kilogram. When we compare it to other similar radial grippers, they have a density of only around 40. So this really shows the advantage of this design methodology for creating very lightweight grippers. And as the prototype is so light, this is like an ideal solution for drone delivery applications. And we could even imagine creating a frame of the drone as another layer to the kinematic stage, making the whole system even more integrated. Thank you very much for your attention. Please don't hesitate to email me if you have any questions.